How is my video? Is it?
Looks like you're in the woods.
Yes, yes. I am in the Santa Cruz Mountains, actually.
Beautiful.
Yeah, so thanks for introduction, and I'm very honored to be a part of this presentation and this talk. I'd like to give you a story about how we're transitioning from one sensor to another and how we measure the benefit and all aspects of designing new camera. So it's like if you were building a new camera, how would you approach this? And my story consists of 4 key parts. The first is how we measure image quality for automotive and for, let's say, for autonomous camera. And the second part is how people measure the quality without using any kind of numeric metrics. And it is how we use our labeling team to label some images and derive a vision trend for 2 sensors and compare the trends. The third part is how to connect the camera to the GPU, basically. So there are multiple ways of doing it, and the ISP is into play. And I will, based on the story of mobile, which evolved in its own way, and try to make a new story for automotive here. And the fourth part is what is ISP and how to build an ISP. And also we'll show you some of our joint work with a company called Fast Video on making a new ISP for 8 megapixel, which is GPU based. So the sensor which we currently use is 2 meg. You can see the spec, 3 micron, and the one we are looking at in this presentation.
Hey, Timofey, you might want to share your screen, please.
Yeah.
Oh, really? I apologize.
We've been enjoying the scenery of the Santa Cruz Mountains, though.
Okay, no problem. So I just covered the agenda. This one. So this is the our lab with contrast resolution chart, and this is the airfield experiment which I am going to describe. So there are 2 sensors which we are comparing, the 8 megapixel and 2 megapixel, which we are looking at, and 2 megapixel is our current sensor. There you see the size, the pixel size, pattern, and actual resolution. Here is the floor plan. So the 8 megapixel is a little larger, but it has 4x resolution if you see the digital map. And the pixel size is pretty much grown 1.5 if you think it as a block. So if the resolution would be the same, then each pixel in the existing sensor could be replaced with a block of 4 pixels, and it will be grow. But they also grew into the depth, so it's 4 pixels against 1 big. And we see how this compares to this and how much growth is this really is. So for image quality, we measure 4 key parameters. First is MTF, or how actually the image is sharp across the field of view. The second is vision test, which is like half human vision, half computer vision. So we want to see what is the lowest line we can see when the cameras are placed at the same distance. The third is contrast resolution, where we measure noise versus the differential signal in each patch of the image spectrum. And the last one is color reproduction, because we don't want to mix yellow and red lights when we are passing the traffic lights. So here we took the same lens, same camera model, same backend, and we upscaled to the same size. And this is what we can see at 2 mega. This is what we can see at 8. So we can see 1, 2, 3 more lines. 3 more lines. We think it's around each line is around 8% of visibility in depth. So if you were to see a human on the 2 megapixel in like, let's say 100 meters, then you would see 108 if you only see this line. But if you see this line, you will see 184 or 124, sorry. And this is a comparison at scale. The next is modulation transfer function. It measures how sharp the image is. And we don't really want it to be like peak sharp, like in cinematic lens, where they like to have a sharp kind of field of sharp image in the middle. And it's okay if we lose sharpness to the end, to the edge. But in automotive, we want a consistent map of sharpness across as much as we want, because for machine learning, they're working on convolutional kernels, which search for features. If you had like a line from center to an edge, then you would need a different convolutional kernel and a different neural path to detect the same feature, which is just going from one place to another, which makes more layers, and computational complexity grows extremely fast. And it's also harder to like detect objects. The third is the dynamic range reproduction. So you see patches which are decreasing in their intensity, and we want to see how many patches we will see before we dip into the full noise. And this is the noise level. So we can see that the dynamic range of the system is 58 dB. Even the sensor manufacturer and all the companies are saying that their camera is like 140 dB. The actual dynamic range of the system with the lens is 60. So it's everybody needs to understand that we don't see that many levels with the camera, because lens has flare and the sensor is not set to the maximum exposure possibility. Next is color reproduction. Basically, we are exploring the RCCB versus RGB here, and we are looking at the patches 14 and 15, which are yellow and red. And this is before we apply color correction, and this is where we apply color correction. What we don't want to see here is this type of pattern, where like on the left chart around 15, this is the color mixing. So it means that the reference points are crossed. So in here we see the yellow and red patch. They're so far away, so we are confident that there will be no misrepresentation of color on the traffic light signal. Here are some images which we captured with the 8 megapixel camera system, and we used software ISP Bion Semiconductor to process these images. So this is our runway where we test new features. This is our like parking lot, and this is where we try to look at the human. The human is standing here, 300 meters away, and then we moved camera 50 meters closer, step by step, unless we could see pedestrian very clearly. And we upscaled the pedestrian, and you can see how he's represented at different distances. So it's hard to even say for me where I can confidently say where it's a pedestrian, but I would say like, let's say 100 meters, I'm quite confident. But some other person can say it's 200. It's an argument. So we decided to, since this image has to go to labelers, and they have to label, we asked labelers. We sent them like images from different distances and asked them to label. But first, you can see the video how the network sees the images when we actually like keeping scale but changing the distance. It's in cinema, it's called dolly zoom effect. So thank you very much. Yeah, the second part of my research is how far we can see 2 versus 8 megapixel. Our new member from Perception is actually did this research. His name is Hao, and he is from cinematic background. So we put targets like deer, mannequins, a bicycle, and ball tire on this runway, and we took pictures from each distance from 500 to 50 meters and captured an image, and then we shuffled these images, send them to labelers and see and ask them, how confident are you what you see is a human? And he would say like from 1 to 5, and we collected many labeling like data like this. Then we removed the one which are extreme, like this one who was like seeing better from who wasn't monotonous, let's say, and then some outliers who are too much from common deviation. And then we formed a smooth trend of vision. So you can see that we can see, like, for example, pedestrian with 2 megapixel, and this is like our confidence raises, consolidated confidence goes to 200. Sorry, it goes to 1 at 200 meters. At 200 meters, we can see the pedestrian. So this is the 1, but we don't have to be at 1. We have to be at somewhere on this slope, because if we go down the slope, we will see false positives and the car will brake. But if we are somewhere like above 0.5, it's very good consolidated confidence for the label. So we can see that we reach 0.5 or 0.6 confidence as like 300, for example. So, and then we did this trend for 8 and for 2 mega, and then we compared, put them against each other. And the green line shows the how much more, like how many times more confident you are, because we measure confidence not incrementally, but logarithmically, you can say, or in time. So like we can see that on average from 600 to 200 meters, we have consolidated confidence, which is 2 times more for 8 megapixel, which is big. If you think in distance, you will have like 0.6 confidence, 50 or 60 meters here in between, which is big for braking and reaction time. So another interesting trend which we derived is how the pixel size compares to the confidence of the labeling. So you can see that 2 mega, since it has a more it is a larger pixel, each pixel actually contributes more to the trend. So we reach the trend of like high confidence much earlier at 10 or like 13 pixels, but in 8 mega we need much more pixels. So computationally we need more pixels and more you can say transistors in the end to detect the same to detect object at the same confidence. So the cost of the system will grow. And here is our Alpha X fleet in China, which is based on Lexus RX 450, and we are currently using a system. I actually wanted to give you a quick history lesson from mobile. So in mobile, the ISP was before I talk to our system architecture, I want to give you a mobile one. Sorry for a little confusion. So where in the times of feature phones, 2004, it was SoC which handled image processing and controlled the sensor from the same board, and then this RGB signal process was sent to GPU or like CPU at that time to display the image. And then at 5 megapixel, I took part of this development with Samsung and Sony. So it was ISP, which was a single chip. And this is how the situation is in mobile, in automotive right now. ISP is usually a single chip sitting near to the camera or maybe on the board, but it's a chip. And later from 8 mega or in mobile, the ISP just became a part of SoC of the GPU with the same RAM and bus, which was like Google driven that kind of architecture by Camera 2, and we worked on that architecture. And right now, this is our Alpha X system on a very top level. So there is ISP in each camera. So this kind of block is a camera module, which is an ISP is a single chip inside of each camera. And then the images are going through sensor gateway to the memory and sent to neural network. And in future architecture of 8 mega, we want the similar concept, because these cameras 8 mega, they need much more processing, and that will heat up the camera much more, because the ISP is the one who is producing the heat. And it makes sense to put ISP. No, I'm not talking about wide angle cameras. I'm just looking about main cameras for driving. The ISP makes sense to put on the GPU, and NVIDIA is doing like that from a long time ago. And basically, the second part of this system, which I wanted to cover, is binning. Sorry for the spelling here, it should be double N. And the binning means that we can, on sensor, change the resolution of the camera to 2 megapixel and output a 2 megapixel image, same, very similar to the image that we have right now, which is 2 megapixels. So we can format it exactly the same size. So the infra doesn't have to really handle so many megapixels. And the thing is that when we are looking to the sides, we don't want to see that far. So 2 megapixels is pretty much good, but we can always switch firmware and upgrade to 8. And the main front cameras, we definitely want 8. So we are working on the infrastructure to how to handle that, and really want to collaborate with other companies to do it. So this is how the process will look like with the raw data. If we collect, because in this design we have to send raw data to the bus, and we always want to save the raw data because it has much more information compared to RGB. So we save it, and then we have two pipelines. One pipeline is for training and one for labeling. For labelers, we use it human vision pipeline. For training, we can optimize anything with the product like Atlas, or I forgot what was the name of the product, but we can even train it because the ISP can be very differentiable. And we can use start from using the same pipeline as we use now. This is an interesting article from which was mentioned by Alexis Lewis from ARM, and it says how ISP actually contributes to the learning process. And like a transistor at ISP is better to put it. Basically, image quality contributes to the learning process more than increasing the network size. So the trend should be reducing the network complexity and increasing image quality, because we want to see nice image quality for the labelers, and we trust the labelers more than we trust the network, because the network is learning from labelers. So how the raw format looks, it looks like this. So each pixel you see just one color information. It's either R, G, or B, and each pixel is packaged into 32-bit word, and then actually maximum is just 2 in the power of 24, which is 16 million, which is like tremendously more than the RGB. So we can have much more data, and we don't want to lose this data. And for this, we build an ISP with fast video, which is consisting just of 3 main blocks: demosicing, tone mapping, and CCM. So tone mapping is actually converting from 24-bit to 8-bit for the network, with retaining most of the information. So we decide what levels are important for us, which are not. And the demosicing is the part which populates all colors. So you can see RGB instead of this type of strange image. So, and this is the pipeline for labeling, and this is the pipeline for CNN. It should be as simple as possible. So we don't want to have a lot of parameters there. Otherwise, we can have, but if we want to learn, we just want to reduce like two parameters to as few as possible. So this is the result of our ISP, and you can see again the vision chart, the Nokia star, and some stickers. So here we were able to reach a better false color suppression and a little sharper. We can see probably like one line or maybe even 2 lines more, just because the demosicing algorithm is more superior. So you can see you can increase, for example, like a system to 8 mega, and you will reach like pretty much the same increase. So, or you can apply better demosicing to your current one. So it's all puts together. And here are some example images. Here we were quite good on noise suppression and also false color suppression. At the scale, the Siemens star, you can see it's less aliasing here. So resolution is definitely increased. You see like the V pattern. So all this builds up at scale and at size. So you see that we can see this line, we can hardly see this line. So it's like increasing maybe like 8% in the visibility. But by switching to 8 mega, we were able to increase 25% pretty much as you compare from the trend. And this is another image. Again, I think it's slightly better color reproduction, but I want to mention that we're not using noise reduction. So we don't use noise reduction for labeling or for any type of processing, because we think that it reduces the accuracy of detection. So yeah, some other image. Yeah, and that's it. I don't know how much on time I was, but thank you very much. If we have questions, this is the time.
Thanks, Timofey. Yeah, I've got plenty of time for questions. There was one that came during your talk asking about which imager manufacturers you're working with.
We're working with
that you were comparing here in this presentation.
This is on semiconductor in this presentation, but we are working with also Sony and OmniVision.
Okay. Okay.
So on semiconductor is our partner, and we develop an ISP with them also for AGI product.
Okay. So on semi. So in the time I was at Ford, toward the end of my tenure there was a lot of work going on with machine learning algorithms for computer vision with the surround view cameras and other things. And the ISP got in the way many, many times of reducing performance. And so I understand the goal of getting that into the learning algorithm for the ISP, but how well does that generalize? Is it specifically trained to do certain things like those eye charts you were showing? Did you train it only on eye chart data?
No, the ISP is field trained. So the more we are currently using AP200 ISP, and we are tuning it based on the issues which we see in the field. So if the car doesn't detect anything, something, or detect something which is not there, or misses a traffic light, the driver will hit the brake, and this will go to the Jira system. The Jira system will classify this issue, and we will see the population of each issue, and then we will tune specifically to reduce this issue and not introduce others. So the ISP right now is trained on the field, but I just know that if we have some charts, we can also train ISP on the charts if we have a real-time tuning. But it's just an idea from the Algalux company, which they promote a lot, but I just wasn't able to explore that because we were not collecting the data which is before ISP. We're collecting it post ISP. So if we missed some information and we didn't capture it, then we missed it. So we have to go to the field, and I have to ask somebody in China and say, can you please to put this setting into the ISP and go to this traffic light at this time, and I hope it will be raining so we can see why we missed the traffic light. Was it the camera which was wet, or it was because the ISP setting exposure time was too short? And then they have to go with the laptop and camera and take this picture because they need to change settings, right? And it's so much work for us and for them, so that if we could, if I had the raw file, I would change several settings, and then I will say, oh, okay, the problem is that ISP, it's not that the ISP didn't process the data correctly, but it didn't capture the data correctly, because ISP is the one who controls the sensor and tells how to capture the information. So if ISP wasn't smart enough to understand how to change the sensor setting, then this is the biggest problem. So we have to retune the ISP. But then retuning ISP is hard, because if we change setting of the ISP, then all the images will come different, and then the network might kind of trip on that, because he didn't expect that other images would change. So if one setting to change, you need to be very careful to deploy that. You have to put it in a testing feature, test it with in a special condition. It's a headache. It would be much easier if we was just able to see the raw data and say if that raw data was captured properly, or we lost the data while processing from the 16 million to 200 level. So this is how I think how it generalizes to. Yeah.
All right. There was a question about a particular slide that you showed.
What's the slide number?
Yeah, let's see. Let's go. Why don't you just go backwards? It has a question about a bus diagram. So
Well, the
probably,
bus diagram is conceptual, so it doesn't really. Yeah, what's the question?
it's not specific enough. The question is about, is it a MIPI or CSI2 interface?
Between the sensor and ISP, it's MIPI, but within the bus, it's already something that I don't know because I'm sitting between the ISP and sensor right now.
Okay. So if the person who asked that, if that covers it, then we're good. And if not,
Yeah,
send
this
us
this
that.
is not the system architecture. What you're looking here, it's basically a conception. It's a mind architecture because like there is sensor gateway and there is FPGA, so there is more things in it. But I just look through it because I think they don't change the image quality. So I'm not touching that, but they definitely affect the latency and speeds. Yeah, one part I didn't mention is the image compression, because when we're saving the raw data, we want to, if we have 8 megapixel cameras in raw format and we put it like continuously save that data, our like data storage will be full in a couple of days, because you understand
Right.
how much. So we need a good raw compression algorithm, which we are like very happy. Who will develop it will be the next like Elon Musk, because it's something which the industry is searching, and Huawei is making a huge compression contests, which I heard of. So I will be watching that very, maybe even send them an image if they can compress it. Like if we maximize the metrics which I described and compress the data, that will be really astonishing for the industry, because we
Right.
can.
Because you need lossless compression, correct?
I can lose, but I want to control the loss. So if I can
Hmm.
control the loss in the trend, or if I can control the loss in the basically on this chart, I don't want to stop losing lines. So if the compression destroys the lowest line, one, and I can control how many lines I want to see, this I'm fine. So, but I have to have a lossless setting as well. So it's very important.
Okay. And the question just popped in regarding compression. And the question is, isn't binning same as compression?
No, binning is losing data. Binning is like you take 4 small buckets and then you destroy the walls between them. So they are like, if you have a one, if you
Can you
look
go to
at this
that slide,
pixel,
please? Yeah.
yeah.
Yeah,
So
you're talking
this is
about.
four pixels, and they have each has a different value. And then binning, it will basically break those walls, so they will all equalize and come into the average value of this two. And it's done like electrically or digitally, but it just crashes the data, and it reduces the quality tremendously. So if we have 8 megapixel beamed to 2, it will have a big pixel which will give us bigger like high dynamic range, but and better SNR maybe, so, not sure, but depends on your exposure settings. But it will definitely reduce the resolution. So because for the same area we will have much less pixels compared to this large pixel, because this pixel is larger when it binned to, and we will lose the resolution and we will go below the original two. We have a study of binning which is very precise, but it's a whole new presentation. So it's basically binning 8 megapixel to 2 will give you like 1.5 megapixel image. So
Okay. Good deal. Thank
in
you.
this sensor, yeah.
Thank you. That covered it. So Timofey, we're at time. We're at the bottom of the hour.
Well, I'm very happy that I fit it in the time.
It worked
This
out
is my,
great. Thank you so
yeah.
much. And have a good rest of your day in California.
Thank you very much. Have a great one.
Cheers.
Bye-bye.
All right, for everybody online, this is 12:30 Eastern Standard Time, and it's time for a half an hour for whatever you need to do, either networking or grabbing a bite to eat or some other thing. And we'll reconvene in 30 minutes at 1 o'clock.
Yes,
Right.
that's correct, Tom. Thank you very much. Yeah, so totally agree. As Tom mentioned, we will now reach our half-an-hour lunch break for those who are on the East Coast. Of course, for all the other attendees, but including, of course, also those coming from the East Coast, it's also definitely worth it now to take the half an hour to explore our event app of the Tech.AD USA, start and initiate networking with the speakers, which have been presented very fantastic way the past 3 days, including those, and a special thank you to those presenting today. So we will be back here at 1 p.m. Eastern Standard Time with another, I guess, wonderful talk, which is going to be contributed by Joyce Farrell, who is the Executive Director at the Stanford Center of Image Systems Engineering at the Stanford University. So see you in half an hour, and thanks for joining us so far.